This video is a lecture on the chi-squared distribution. The chi-squared distribution we're going to be using for three different statistical tests. The first test we'll use is called the goodness of fit test, which tests to find out whether a distribution of an unknown population fits a known distribution. The second test we'll be looking at is the chi-squared test for independence, which tests to find out whether two different categories are independent of each other. And then finally, we're going to be looking at what's called the test for homogeneity, which tests to find out whether two different unknown populations have the same distribution as each other. So the chi-squared distribution, just like other distributions we've looked at, the normal distribution, or the uniform distribution, or the t-distribution, all of these distributions have a curve associated to them, and the area under the curve gives you a probability. And similar to the t-distribution, for the chi-squared distribution, there is a degrees of freedom that will tell us what that distribution specifically looks like geometrically. We're not going to need that too much when we use our calculator, but it's good to know so that when we're thinking about rejection regions and what we're doing, what we're looking at is if it's far enough to the right, it turns out, then we'll reject the null hypothesis. And if the test statistic is not so far to the right, then we're going to fail to reject the null hypothesis. So I have three of these written out. If we have 5 degrees of freedom, then the curve looks like this. Notice that it is unimodal. It is highly skewed to the right. You'll also notice that there are no negative values. Since this is the chi-squared distribution, there's squaring going on, which we'll see in a minute, and negatives won't happen. For 10 degrees of freedom, it is also unimodal. It gets still skewed right, but not quite as badly. And then for 15 degrees of freedom, it is unimodal and it's less skewed right. It's very close to looking somewhat normal when we get up into the higher degrees of freedom. We're not going to be using this too much, but it's good to see where these analyses are coming from instead of just trusting our calculator, which we're going to do some. But it's good to see that there's an actual distribution we're looking at. So let's move on and talk about how the chi-squared statistic is actually found. So what it actually measures is how far the observed counts from the sample are from the expected counts. So what we typically do is we take a survey or we collect data, and with a chi-squared, what we're going to be looking at is data that is qualitative. Things like, what state were you born in? Or what is your race? Many, many different qualitative data values can happen. And we're going to be looking at the frequencies for each answer that could happen. And we can get, based on that qualitative distribution, you can draw a bar chart, for example, and we can look at that and we can have expected frequencies versus what we actually saw. So for example, if you're going to roll a die, and the die was just a 6-sided die, then you expect that 1/6 of the rolls should be 1s, 1/6 should be 2s, etc., all the way up to 6. 1/6 of the rolls should be a 6. Well, if you roll a die, say 50 times, then you're not going to get exactly 1/6 of being each. In fact, you couldn't with 50 rolls because 6 doesn't go into 50. You're going to get something somewhat close to 1/6 of 50. So if it's a cheating die, you would think that maybe it's not going to be that close, whereas if it's not cheating, then it should be pretty close. So what the chi-squared distribution does is it measures how far off what we observed is from what we would expect if the die was really true. The formula for that, it's a little bit complicated, is that chi-squared is the sigma, if you remember, that's the sum. You take what you observed minus what you expected, you square that quantity and divide it by what you expected. So for example, if you rolled, say, 60 dice, then you would expect 1/6 of those to land in each number, or you should get 10 ones, 10 twos, 10 threes, 10 fours, 10 fives, and 10 sixes. So each of them should be 10. But if you rolled a die 60 times, or 60 dice, you probably won't get exactly 10 ones. You might get 9. You wouldn't be so surprised. And then that observed minus expected would be 1. Or if, say, you got 12, the observed minus expected would be 2 or -2, but when you squared it, you would get 4. So squaring helps it so that if you're far from the expected, then you're still going to end up with a positive number. And then dividing by the expected, that helps give us some kind of weighted average is what's going on here. So that's a formula. We're not going to be actually calculating with the formula by hand. I'm going to use a calculator for that. But I think it's a good idea to say, here's the data. Let's look at it. Does it look like we're far from the expected? If so, then these differences are going to be big, and you're going to have a big chi-squared. Or are the observed pretty close to the expected? So expected 10, we observed 11. That's just one away, not a big number, and you're going to get a small chi-squared. On the other hand, if you expected a 10 and you got a 25, then observed minus expected is 15. Square that is 225, and that's really big, and you get a large chi-squared. So chi-squared measures how far the observed is from the expected in a way. So now let's use it. So we're going to start using it by what's called the goodness of fit test. And what the goodness of fit tests is, it tests to see if a distribution fits a known or expected distribution. So for the die example, our expected distribution in that case is a uniform distribution. You should get exactly 1/6 for every single die roll. Well, our observed distribution may not fit that. And the question is it uniform or is it not uniform? You can say the same thing with the normal distribution. Does it seem to fit a normal distribution? Is it unimodal? Is it skewed left, skewed right? And we'll have an example of that. Or sometimes it'll be a distribution that is some known distribution. Maybe the Census Bureau has taken the data and we know what it is for the state of California, and we want to find out our local area. Does our local area fit the California's area? And all we have is a sample for the local area. So notice that for the chi-squared goodness of fit test, there is only one population at which we've taken a sample from, and we're comparing that to a known population distribution. So one of the nice things about the goodness of fit test is we don't have any assumptions that are needed. Of course, you got to have random sampling. Nothing ever happens in statistics if you have biased sampling. That's never okay. But given that we have random sampling, you do want the sample size to be reasonable. Typically, you want to make sure that all of the expected counts are at least bigger than 5 is a good idea. Some people use 10, but 5 is often good enough. So again, we use the goodness of fit test to see if a distribution is normal, or maybe to see if it's uniform, or does it fit some population that we know about from, say, Census Bureau, or maybe past experience that we know what the population should be. So in any hypothesis test, there's a null hypothesis, and there's an alternative hypothesis. The null hypothesis for the goodness of fit test is the distribution fits the given distribution. Of course, we're not going to just say the distribution fits the given distribution. We might say the distribution is uniform, or the distribution of our town, or maybe our age distribution for our town, is the same as the distribution of the United States. That might be an example of H0. On the other hand, H1 is the opposite, which means that the distribution does not fit the given distribution. So maybe it isn't a normal distribution. So you check it. Is it normal? Is it not normal? Well, as we've seen, we're going to be able to show that maybe it's not normal. We won't show that it is normal, because you never accept H0, you only accept H1. The goodness of fit test, here's the bad news for some of you, is that I've been presenting on the TI-84 calculator. The first bad news is if you have a TI-83 or 83 plus calculator, then you probably don't have the goodness of fit test on your calculator. It can be downloaded onto your calculator. You can go to the internet. If you happen to know me, then you can download it from me and I'll help you out. If you're at a different class or different school, you're going to have to go find someone who's got it so you can download it, or you're going to have to program it yourself. There's some good YouTube videos on how to program the goodness of fit test. In the one that comes with the calculator, if you have a TI-84 plus, you still may not have it, and you still may need to download it. It's one of those weird things that for Texas Instruments, I guess they realized that they needed it halfway through production of the TI-84s. So the older TI-84 pluses don't have it, and the newer ones do have it. So you're just going to have to go into your calculator, and I'll show you how to do that and see if you have it. If you're using the newer calculator that does have the goodness of fit test, then it's going to ask you what are the degrees of freedom. So we've seen that before when we had a t-test. If you remember, for a t-test, the degrees of freedom was the sample size minus 1. On the other hand, the degrees of freedom for the goodness of fit test is going to be the number of categories minus 1. So for example, if you threw 60 dice, and you looked at how many ones, how many twos, all the way up to sixes you got, and you wanted to do a goodness of fit test, it's not going to be 59 for the degrees of freedom. That would be the sample size minus 1. It's going to be 6 minus 1, because there's 6 categories. You can roll a 1, a 2, a 3, a 4, a 5, or a 6. 6 minus 1 is 5. So you would say that there are 5 degrees of freedom if you're rolling a die. So we'll see some examples of this. So here's my first example, and it says the following. 55% of South Lake Tahoe residents are white, 22% are Hispanic, and 23% are of other races. I did this a few years ago. It might be outdated, so don't get mad at me if it's changed since. But at one point, this was true. The table below shows the results of a study of 300 randomly selected Lake Tahoe Community College students. The question is the racial composition of LTCC students different from that of South Lake Tahoe? So notice that the survey question here is qualitative. It is, what is your race? And your answer might be, I'm Hispanic, or I'm white, or I'm some other race. It's not going to be, my race is 76. There's no number here. And it's not a yes or no question either. So because of that, we can't use prior types of tests we've used. We're going to use the goodness of fit test because we're testing to see if the distribution of races of this unknown population, the LTCC population, is the same as the known population, which might have come from the Census Bureau, of South Lake Tahoe residents. Because of that, it's a goodness of fit test. And here are the numbers in this study, and of course this is fictitious, but imagine a study was done. Then this study that could have been done, that they got 180 students that were white, 51 were Hispanic, and 69 were from other races. So the question is this the same distribution for LTCC as the known distribution of South Lake Tahoe? So what we're going to do is we are going to first form our null hypothesis and our alternative hypothesis. So the null hypothesis, H naught, is the racial distribution at LTCC is the same as it is in South Lake Tahoe. For H1 is the racial distribution at LTCC is not the same as it is in South Lake Tahoe. So notice some key words in both H0 and H1. The word distribution always has to be there when you're doing a goodness of fit test. Also for H0 is always the distribution is the same as what's expected, and H1 is that it's not the same as what's expected. So that's H0 and H1. So what we need to do now is use our calculator to perform the goodness of fit test. Because we want a p-value, and when you get a p-value, we're going to be able to decide whether to reject or to fail to reject the null hypothesis. So let's go to our calculator. So here's the calculator. So for a goodness of fit test, I have to start by entering my data. So I go to Stat, Edit, so Enter. I clear out my L1 and L2. And then for L1, I want to put in the observed counts for each of the categories. So I had 180 white students. So I type in 180, hit Enter, then 51, Enter, and 69, Enter. For L2, I put in the expected counts. Notice we had 300 students total. That was our sample size. And we expect 55% to be white if LTCC follows the same distribution as South Lake Tahoe. So 55% of 300 I find by typing 0.55 times 300. Hit Enter. And notice that's 165. So note, by the way, that our observed was 180. Our expected was 165. It's not exactly the same. It's not that far off. But the question is it far away enough from what was expected to be able to reject the null hypothesis? That's what all this calculation that the calculator is going to do for us will show us. So for the expected Hispanic count, we had 22% Hispanic. So I type in 0.22 times 300, Enter, and I had 23% were other. So I had 66 Hispanics. Let's find out how many others that we would expect to have. So 0.23 times 300. Hit Enter, and notice that for the others, it was right on. 69 was expected, and 69 is what was observed. So notice we're off a little bit for the whites and Hispanics, but we're right on for the other. Again, just by looking at those numbers, it's hard to tell whether that's far away enough from what's expected. And that's what the test statistic is all about. So let's go to Stat again. I go to Tests. Turns out that it's a lot faster to use your up arrow. And this is where you cross your fingers and hope you have it. So the test you want is right here, called the chi-squared GOF test. If you have it in the calculator, you're golden. If you don't, you're going to have to download it. So I have it, so I am golden. I'm lucky. I hit Enter on that. And the observed, you want to make sure it says L1, because that's what we chose to be the observed. If it's not, make sure you put in L1, which is second one. For the expected, it should be L2. So degrees of freedom, on the other hand, remember that was number of categories minus 1. There are 1, 2, 3 categories. 3 minus 1 is 2. So the degrees of freedom is 2. I just go to Calculate and hit Enter. And here we have it. Notice that the chi-squared, by the way, this is not an X. This is the Greek letter chi. And that's what it looks like. And the test statistic is chi-squared equals 4.77 about. And the p-value is about 0.09. So typically we use 0.05 to see if we have evidence to reject the null hypothesis. 0.09 is bigger than 0.05. So notice that we didn't reject the null hypothesis. We failed to reject the null hypothesis. Let me go back to the PowerPoint, and then we'll talk about how to finish up the problem. Okay, so here's the PowerPoint, and here's how we make our conclusion. What we can say is there is insufficient evidence. Remember, our p-value is about 0.09, too big, so that means insufficient evidence to make a conclusion about whether or not the racial composition of LTCC students is different from that of South Lake Tahoe. So this is a very fancy way of saying we did all this work, we asked 300 students, and we know nothing. So it's kind of a drag. So all we say is we have insufficient evidence to make a conclusion about whether or not the racial composition of LTCC students is different from that of South Lake Tahoe. The distributions might be the same, the distributions might be different. We really don't know. So let's look at another example. So here's the example I have now. Does it matter what season a person was born in when it comes to getting into UCLA? Of the 400 Bruins, that's the name of UCLA's team, so I'll call them Bruins, who were surveyed, 93 were born in the winter, 95 in the spring, 126 in the summer, and 87 in the fall. Off the subject, I'm a Bruin, and I was born in the summer. So I guess I made these numbers up. I decided, there's probably a lot of summer people like me. If you want to do the study, you would go and randomly survey 400 Bruins, UCLA Bruins, and come up with your numbers. So H0, the null hypothesis. In this case, if it doesn't matter what season a person was born in, that means all seasons should have the same percentage of Bruins. In other words, it should be a 1/4, 1/4, 1/4, 1/4 split for spring, summer, winter, and fall. So H0 is the distribution of seasons that Bruins were born in is uniform. Because remember, uniform means all the same for each of the categories. H1 is the distribution of seasons that Bruins were born in is not uniform. So what we need to do is we need to use our calculator to decide whether or not we have evidence to say that the distribution of seasons that Bruins were born in is not uniform. Okay, so we're back in the calculator. And notice this is a goodness of fit test because we're testing to see if an unknown distribution, that's the distribution of Bruins in terms of the season they were born in, fits the uniform distribution, which is the known uniform distribution. So I'm going to go to Stat, Edit. I got to clear out L1 and L2. And let's put in the observed counts for each of the seasons. For the sample, there were 93 for winter, 95 for spring, 126 for summer, and 87 for fall. For L2, that's our expected. Notice that we have 400 in our sample. Well, if we have a uniform distribution, that means spring, summer, winter, and fall should have equal number of Bruins. Well, if there's 400 total Bruins, and if they split into 4 seasons, then you're going to have 1/4 of 400, or 25% of 400. You could do it in your calculator, but hopefully you know that 1/4 of 400 is just 100. So for the winter, you expect 100 Bruins that were born in winter. You would expect 100 that were born in the spring. You would expect 100 that were born in the summer. And you would expect 100 that were born in the fall. So whenever you have a uniform distribution, all the expected numbers are going to be the same. That's what uniform is all about. So now I go to Stat. I go to Tests. I go up to my chi-squared GOF test. Notice that is not the same as chi-squared test. If you have chi-squared test in your calculator and you do not have chi-squared GOF test, then you're screwed, basically. You have to download the program. So make sure you're doing chi-squared GOF test and not chi-square test. So I hit enter. Observed is L1, expected is L2. There are 4 seasons. 4 minus 1 is 3 now, so degrees of freedom is 3. I go to calculate, and there we have it. The chi-squared test statistic is chi-squared equals 9.19. The p-value is 0.026868854. So in particular, it's around 0.03. I've been using 0.05 as the level of significance. So notice that our p-value is small compared to that. So let's go back to the PowerPoint and give our interpretation. So here's the PowerPoint. So remember, we had a p-value that was really small, 0.03. So that means we get to reject the null hypothesis and accept the alternative hypothesis. And we can conclude there is statistically significant evidence to conclude that the distribution of seasons that Bruins were born in is not uniform. Notice that our conclusion says nothing else. It does not say necessarily who the culprit is in not being uniform. It might be there were not enough in the fall. It might be there were too many in the summer. This chi-square distribution does not say which is the problem season. It only says that it's not uniform. Not all seasons are the same in terms of the population of all UCLA Bruins. Not the 400 Bruins, but all UCLA Bruins is what we've made our conclusion about. It's always about the population, not about the sample. Okay, so let's go to another example. So here we have, again, 400 students. We're asked how many pairs of shoes they owned. Their mean was 12.1, and the standard deviation was 5. Below gives a frequency table of the results. Is there evidence to suggest that the distribution is not normal? So we have seen before a lot of times when you don't have a normal distribution, you're not able to do a certain test, especially if you have a small sample size. On the other hand, if you do have a normal distribution, you can perform a test. So this is one way. There are other ways, more sophisticated ways of testing for normality, but this is one way, kind of a simple way. And that is using the goodness of fit test. So let's write down our null and alternative hypotheses. So the null hypothesis, H naught, is the distribution of the number of shoes owned is normal. It fits the distribution. That means is normal. Our H1 is the distribution of the number of shoes owned is not normal. Doesn't fit the distribution. Okay, so now let's go to our calculator, and that's going to be a little tricky on how to decide what to put in for the expected, but I'll show you in a second. Okay, so here's the calculator. Let's go to Stat, Edit, clear out L1 and L2. And now for the observed, L1, I'm going to put in the observed numbers, 100, 120, 115, and 65. So 100, 120, 115, and 65. Okay, L2 is a little tricky. Here's where we have to remember how the normal curve works. Well, notice that the mean is 12.1. The standard deviation is 5. So if we add 5, add the standard deviation to the mean, you get 5 plus 12.1, which just happens to be 17.1. This was not some weird number I threw in. If you subtract 5 from 12.1, 12.1 minus 5 is 7.1. So notice that these ranges, 7.1 to 12.1, that means within one standard deviation of the mean and to the left. 12.1 to 17.1 means within one standard deviation of the mean and to the right. Well, we know from the empirical rule that within one standard deviation of the mean, we should expect 68% of the data to lie within 1 standard deviation of the mean. Well, if you just want the left-hand side of that, that'll be half of that. Well, half of 68% is 34%. So we would expect 34% of the sample to lie within 7.1 and 12.1. So that means in these two intervals here between 7.1 and 12.1 and between 12.1 and 17.1, because of symmetry of normal distributions, that should be 34% of the data each. Well, if 68% is inside, then 1 minus that, 1 minus 68%, is 32%. That means 32% is outside. But to the far left will be half of that, because half is on the left, half is on the right. It's symmetric. Half of 32% is 16%. So we would expect 16% to be in this first interval, 0 to 7.1. Negative infinity to 7.1. Negative is not going to happen when it comes to pairs of shoes owned. So I'm just going to call it 0 to 7.1. And there should also be 16% above 17.1. So now I'm ready. I can type in 0.16, that's 16%, times 400. And I get 64. Remember, we had 34% that should be in between 7.1 and 12.1. So that's 0.34 times 400. Enter. And I get 136. Because of symmetry, we're going to have 136 for the next interval between 12.1 and 17.1. And we should have 64 greater than 17.1. So those are our expected counts. And we could see the expected and observed are not exactly the same. The question is, are they far enough from each other? And that's what the chi-squared good as a fit test will help us find out. So I go to stat, tests. I go up a bunch till I get to chi-squared GOF test. I hit enter. Observed is L1. Expected is L2. Notice there are 4 categories here. 4 minus 1 is 3, so degrees of freedom is still 3. I go to calculate and hit enter. And there we have it. Our chi-squared value is 25.39 about. Notice a p-value is not 1.28. Don't forget about this e negative 5. Our p-value is 0.00000128 about. So our p-value is absolutely minusculely small. So that means when we have a p-value that's tiny, we reject the null hypothesis. So let's go back to the PowerPoint. Okay, so here's the PowerPoint, and we had a really tiny p-value. So what we can say is there is statistically significant evidence to conclude that the distribution of the numbers of shoes owned is not normal. Okay, again, we don't know why it's not normal, but we do know with very strong evidence, because we had such a tiny p-value, that the distribution is not normal. Okay, so let's move on to the next kind of test. So the next test I want to talk about is the chi-squared test for independence. What it does is it tests to see if 2 variables are independent or dependent. Again, similarly to the other chi-squared test for good as a fit, with the chi-squared test for independence, no assumptions are needed, other than random sampling, of course. You never want bias. And also, you want to make sure the expected counts, and we'll see what that means, should be greater than 5. You need a pretty large sample size. H naught, the null hypothesis, is the 2 categories are independent. H1 is that the 2 categories are dependent. So let's look at what to do with the calculator. So in particular, the TI-84 and also the 83, you're in good shape with the test for independence. Both of those have the test for independence on it. And what we do is we're going to go to matrix. We haven't seen that before. I'll show you in a little bit. And then edit. Select the number of rows and columns, and then enter the data. Then we're going to go to that chi-squared test, the one that was just above the chi-squared GOF test. They are different. So we go to the chi-squared test. The observed will be the matrix A. The expected will be the matrix B. Then, as usual, we hit calculator, and the rest is the same. We look for the p-value and make our conclusion. So let's look at an example. So here's the example I have. 1,000 Americans were asked their political affiliation and their level of education. Is there evidence to suggest that political affiliation and education level are dependent? So here's the data I collected, or at least I pretended to collect. So pretend I asked 1,000 people, and here's what I got. I got 62 people said that they were Democrats, and they had less than a high school education, for example. Over here I had 131 Republicans who were college graduates. So we could see all the data, and notice that it's in a table. Also, we call that a matrix. We've seen this table before, and we've even seen independents. It turns out they're not a coincidence that we've seen them and that we're going to be able to do this. These are called contingency tables. And we learned about independence for, say, Republican is independent of being a high school grad. We were able to do that. And it turns out in the detailed calculation of the chi-squared, the expected count has a lot to do with the way we tested for independence for one specific group, Republican versus high school grad. And each of the expected is calculated kind of in that way. I'm not going to go into the details here in this lecture. I'll let you look them up if you want. So let's write down our H naught. Our H naught is that political affiliation and education are independent. And H1 is that political affiliation and education are dependent. So now that we have H naught and H1, we need to go to our calculator. So let's do that. Okay, so here's the calculator. And as I mentioned before, I'm going to go to second matrix. That's right here. It's the one above that little x to the negative 1. Notice this is a new screen. I'm going to go over to the right twice to edit. Hit enter on A. And the number of rows we had were 3. Democrat, Republican, and Independent. So 3, and hit enter. The number of columns we have were 4. Less than high school grad, college grad, and post-college grad. So 4, and hit enter. Now what I do is I put in all the numbers. So I type in 62, hit enter. I type in 240, hit enter. I type in 81, hit enter. Type in 35, enter. Notice it goes to the next row. I type in 56, hit enter. And then finally, I type in 12. That's our last one. I've typed in all of them in my matrix. Hit enter. And I have my matrix entered in. Now I go to stat. I go to tests. Up arrow again is easier. So I'm going to go up until I get to the chi-squared test. Notice this is different than the goodness of fit test. I'm going to use the chi-squared test to test for independence. So I hit enter. It says observed A. You got to make sure that says A. If not, you got to put in A matrix. Enter. Expected is B. Enter. And then calculate. I hit enter on calculate. Okay, and there we have it. Our chi-squared is 29.34 about. That's a test statistic. The p-value is not 5.25 because of the e negative 5. It's 0.0000525, which is, again, really, really tiny. So that means that we have very strong evidence to reject the null hypothesis. So I am going to go back to my PowerPoint and state my conclusion. Okay, so here's my PowerPoint. I had a really tiny p-value. which means I rejected the null hypothesis, and I can say there is statistically significant evidence, very strong evidence, to conclude that political affiliation and level of education are dependent. So let me show you one more example that I want to show you one that uses a computer just so you can see what computer readouts might look like. So a study was done to see if college major and housing type are dependent. What can be concluded at the 0.05 level of significance? So here is the table that I had entered in, and I used a computer this time just to show you what it might look like. And the main thing is that you'll see that it says contingency table results. We have our statistic as chi-squared. Here's our degrees of freedom. We're not worried about that. It's just going to compute that for us. We have our chi-squared value. That's the test statistic, is 96.7 about. And our p-value just says less than 0.0001. Very small p-value, so that means we reject the null hypothesis. And remember, the null hypothesis, in this case, is college major and housing type are independent. Independent is always in the null. And the alternative hypothesis is that college major and housing type are dependent. Since we had a small p-value, we say there is statistically significant evidence to conclude that college major and housing type are dependent. If the p-value had been larger, like say 0.72, then we would just say we don't have evidence. We have insufficient evidence to make a conclusion about whether they're independent or dependent. But we did have a small p-value, so we really could say that we have statistically significant evidence that college major and housing type are dependent. Okay, the next and final tests that we're going to do in this lecture are a test for homogeneity. What that does is it tests to see if two unknown populations have the same distribution as each other. Very different than chi-squared good as a fit. Chi-squared good as a fit is you have a known population, and you want to see if an unknown population is the same as a known. For homogeneity, neither are known, and you're comparing them. H naught is the two populations have the same distribution. These are both unknown populations, have the same distribution as each other. And H1 is the two populations have different distributions. For the calculator, it turns out that the way you use your calculator for homogeneity tests is exactly the same as the way you use it for a independence test. And this is where some of the confusion is. What you're testing is somewhat similar to goodness of fit in that you're testing about distributions, but it's different in that for goodness of fit, one you know, one you don't know. For homogeneity, you don't know either. For independence, the test itself is very different in terms of what you're testing. Testing to see if they're related or independent is very different than testing to see if the distributions are the same. But the calculation work on the calculator is exactly the same. So you go to matrix edit. It turns out for homogeneity, you always have two rows. And then n will be the number of categories. I'll show you how that works. So that's your number of columns. Then we put in our data. Then we go to stat, test, chi-squared test. And it's just the same as we've done before. The observed is A, the expected is B. We hit calculate, and we're golden. So here's an example. 200 statistics students were asked how much they agreed with the following two statements. First, my grade reflects the amount of work I have put into this course. Second, my learning reflects the amount of work I have put into this course. Okay, the hope is that people would agree with both, that if they work hard, they get a good grade, and they work hard, they learn a lot. But the question here is not, do we think that hard work means a good grade and hard work means lots of learning? The question is, are the answers the same for the two questions? So the table below, which I'll show you in a minute, shows the results. So this particular study was done, at least fictitiously, with a what's called a 4-point Likert scale: strongly agree, agree, disagree, or strongly disagree. And the first row is going to be the answers to the grade reflects the work was done. And the second is that the learning reflects the work that was done. And here is the data. Notice that they're not all the same numbers, right? We have a 72 and a 61, a 20 and a 34. Are they different enough? So this is going to be a chi-squared test for homogeneity because we have two different survey questions. We don't know the population for either. We just have samples for both. We want to find out if the distributions are the same as each other. What can be concluded at the 5% level of significance? So first, the null hypothesis is the distributions of the answers to the two questions are the same. And the alternative hypothesis is the distributions of the answers to the two questions are not the same. So we're going to go to the calculator and we're going to do just like what we did for independence. Notice the H0 and H1 are very different, but the calculations will be identical. Okay, so here's our calculator. I go to second, matrix. I go to edit, hit enter. There are two rows, always two rows for homogeneity. So 2 and enter. Here we have, notice, 4 columns. Strongly agree, disagree, strongly disagree. So 4 is good, hit enter. Now I put in my numbers. 67, 72, enter, 41, 20, 55, 61, 40, and finally 34. Hit enter, and now I have my matrix entered in. So let us go to stat, tests, and then up arrow. And again, it's chi-squared test. I hit enter. My observed is A. My expected is B. That's fine. And I hit enter. And here we have it. The chi-squared test statistic is 5.48 about. And the p-value is about 0.14. That's a really big p-value. So way bigger than 0.05. So when you have a big p-value, we fail to reject the null hypothesis. So let's go to the PowerPoint and come up with the conclusion. Okay, so we had a pretty big p-value, if you remember, much bigger than 0.05. So the conclusion is there is insufficient evidence to make a conclusion about whether or not the distributions of answers to the two questions are the same. We just don't know anything, really. We did all this work, and we know nothing. Okay, so here's another example. So a survey was done asking a bunch of college students, are they a man or a woman? What is their gender? And what is their major? And here's the contingency table that shows that. And the question is, at the 5% level of significance, can it be concluded that there is a difference in the distribution of majors for men and women? Let's state the null and alternative hypotheses. So the null hypothesis is that the distributions of majors are the same for men and women. And the alternative hypothesis, H1, is the distribution of majors for men differs from the distribution of majors for women. So let's go to our calculator. So here's a calculator. Just like before, we're going to go to second, matrix, edit, enter. Number of rows is 2. Columns are 1, 2, 3, 4, 5. So 5 columns. And just type in the numbers. I have 68, 21, and then finally 45. Now that I have my matrix entered in, I go to Stat, then Tests. I use my up arrow until I get to chi-squared test. Hit Enter. The observed is A, the expected is B. I hit Calculate, and there we have it. The chi-squared test statistic is 10.33 about, and the p-value is 0.035 or so. So notice that, again, we're using 0.05 kind of as our standard. If it doesn't say, use 0.05. So that means that 0.035 is smaller than 0.05, so we can reject the null hypothesis. So let's go back to the PowerPoint and give our final conclusion for this particular lecture. Okay, so remember we had a p-value of about 0.035, and our alpha we're using is 0.05, small p-value, so that means we reject the null hypothesis, accept the alternative hypothesis, and we can say that there is statistically significant evidence to conclude that the distribution of majors for men differs from the distribution of majors for women. So that's the last example I have for chi-squared tests. I hope this made sense to you. If not, please come and ask me questions. If you're my student, definitely come and ask me questions. If you have another instructor, if you're coming from somewhere else, please ask that person questions. Hopefully they'll be able to help you also. And hopefully this helped a lot and you understand the chi-squared distribution a lot better than you did before you watched this. That's the end of this video, and have a wonderful morning, day, evening, whenever you're watching this. Goodbye, everybody.